Okay, so I'm going to talk about attribute grammars in Erlang. So the work that I'm going to present is done together with Ulf, who just left. And to be fair, Ulf has just done most of the work. So, but I will take full responsibility. So and full credit, absolutely. No, Ulf needed someone to try out this system on, and I've spent a couple of years in Utrecht, and they do some work on attribute grammars as well. So I've been exposed to attribute grammars, and Ulf would make use of that. And it was a task that I gladly accepted because I like working on attribute grammars. So what are attribute grammars? So a formal grammar describes the structure, so the syntax of a language, and attribute grammars can be used to define the semantics of a language. So we can annotate a formal grammar with attributes that we're interested in. A different way of looking at attribute grammars is that they are description of tree traversals, large folds and maps. There are three kinds of attributes. You have inherited attributes that gets pushed down the data structure, and you have synthesized attributes that go from the leaves of a data structure up to the top and are combined at every node in a certain way and are returned as a result. And you may have attributes that are inherited as well as synthesized, and they are called chained attributes. And they can be seen as attributes that are threaded through a data structure. So to show a picture to make it even more clear. So here we have a binary tree, we have a node with two subtrees, which are leaves. So inherited attributes get pushed down from the top, from the parent node to the node, and get distributed to all the children. Whereas synthesized attributes, they are collected from the leaves up to the node, combined in a particular way, and then pushed up to the parent. Or if we are at the root, then it's the result of a particular calculation. And then we have chained. So a chained attribute gets pushed down from the parent. If we can chain from left to right or from right to left, this is from left to right, then we push the attribute to the left child, and then it goes back up again to the parent node. We go back down again, up again, and then give it to the parent node. So why do we want to use attribute grammars? So the attributes can be described on their own while still making use of the values of different attributes. So that allows for modular development. So if you're dealing with a large data structure where information is flowing up and down the tree, while keeping track of the information, well, it can be hard. It sometimes requires a lot of bookkeeping. And if you can separate that into attributes, well, it makes life easier. So an attribute grammar also describes the tree traversal, so you don't have to write the code that does the actual traversal of the tree. That reduces boilerplates. So attribute grammars are often used in compiler-related areas, so scope and type checking, transformations of the abstract syntax tree, renaming, alpha renaming, for instance, code generation and pretty printing.
So just for us that are not super into compilers.
Yeah.
With the scope checking there, you would be at some point you'd know which variables are in scope. And
Yes.
you have an expression that doesn't use a variable that's not in there, and then you get the not in scope and what the hell are you thinking?
The unsafe error message.
Yeah. That's the kind of thing you use this for.
Yeah. Could use it for. So that's the more the traditional area, and well, we have used it for generating Erlang programs.
What kind of an attribute would you use for scope checking?
So typical, I have an example of that, but a typical attribute would be the bound variables. So the variables that are bound. That depends on your scoping rules, of course. So if you have very simple language, it's inherited. Then you just push it down. Then if you have a lambda, then you just push it down. But I have a more elaborate example on that. So we have Ulf has implemented an attribute grammar system, and I helped him a bit, and it's written in Erlang, so that's really good. We have a special purpose syntax for attributes, a really nice syntax that gets parsed, transformed into a formula that we can use internally. Some people giggle, so don't ask just now. I will explain more about the special purpose syntax in a minute. And traditional attribute grammar systems support maps and folds, but our system also supports unfolds that we can use for generating data. So that was why we started out with implementing the attribute grammar system. We want to generate data. And so the rest of the talk, I will give you 3 examples. We start with binary trees, archetypal example, and then I'll show some data generation. And then we're going to do some scope checking for a small subset of the Erlang syntax. So we have the binary trees again. So suppose we want to sum all the values of the leaves. We can do that by writing a sum attribute. So here's the type signature of trees. We have an example value of a tree. And here is our first attribute. So there we see the nice special purpose syntax. So we say in the attribute sum in case of a leaf, then we write, so it's a synthesized attribute. So we write stuff to the parent tree. We write the value n to the parent tree. So the out here means we write to the parent. So these, in the case of a node, we have a left and right tree. These are not actual values. Those are placeholders for the left and right tree. You cannot pattern match on that, but you can query them for attributes. So what this says, well, give me the value of the sum attribute of the left tree. And add that. So when we're going to write to the parent tree again, add it to the value of the sum attribute from the right tree, and output that to the parent node. Well, it's a really concise definition of summing all the leaves in the tree. And we have some more examples. So on the previous slide, we wrote to the sum out, so that to the parent node. So it's quite tedious to write that every time and again. So it's optional. You don't have to specify it. So then, if you omit it, then the last statement gets written to the parent. So this is a more slimmed down version. Then we don't write to out, but say, okay, this is the n as the result that gets written to the parent node. And in this case, if you have a small data type, then you can list all the different possibilities. But if you have large data types, you don't want to write it for every case. And then we can use general rules. And just this general rule says for every other term, then we are going to collect all the values of the sum1 attribute in a list. And that gets written to the parent. I believe I have an. So this gets expanded into this form.
So it needs to know a lot about the type you are traversing. You need to know something about the type of X here, right? To do this.
Yes.
Do you have to put that type definition?
No.
So the parse transform can
Yeah,
work without knowing the type.
yeah. So this was a question for Ulf.
So it magically knows what is working.
Yes. No, we don't need a type annotation. So yeah, I'm thinking about how did we solve it. I have to look into the code. Okay, but it's get expanded in this way anyway. I'm thinking, yeah, now we're using it as an unfold, and then we have the value, and then we know we have a pattern function which tells us. So we have some magic going on. So we need to know what to traverse, and we use a pattern function for that. And we have a standard pattern function, so for that works in most cases, which I will explain it in a bit. So it determines what to traverse in a data structure. So in this case, we're going to traverse over these substructures and not over an integer. So we have another attribute that we define. So this attribute calculates the depth of a tree. So and the depth is an example of an inherited attribute. So we have to give inherited attributes a start value, because if we're in the root of a data structure, then we must have something that we can distribute to the children. So and we use the initial keyword for that. So initially it's 0, and then we have a general rule again. Let's say for every substructure, write to the children the depth of this node added with 1, and this gets expanded again in a similar manner. So the third attribute, called index, is an example of a chained attribute. So chained is inherited as well as synthesized, but it's inherited, so we have to have an initial value. So in case of a leaf, we're going to increase the index that we're going to give to the parent node, and otherwise we're going to chain the attribute through the rest of the data structure. And then we use the keyword chain to indicate that this is a chained attribute. And this gets expanded as follows. So first we write the value to the left tree, then we get back the value from the left tree, and we write it to the right tree, and then we return the value from the right tree upwards. So we can use the index to give a unique number on every leaf. Another feature that the attribute grammar system has is to use local attributes. So we introduce a local attribute with this directive. Otherwise, the parse transform needs to know that this is not a function, but it's an attribute. So, and an attribute can come from somewhere else. If you specify an attribute in a different model, you also need to tell the system, well, this is an attribute, it's not a function. So, and what the relabel attribute does, it replaces the integer with the label of that, the value of the label at that current leaf, and leaves the rest intact. So if we have a sample tree, we can compute the values, so the synthesized values, with the following function. So the module is called EQC-AG. It exports a compute function that takes a list of attributes and the tree to traverse, so the data structure to traverse. And in this case, we give it the relabel attribute, and then we, with the global function, we can define a global attribute. It's an inherited attribute that's being pushed down the tree. And we give it a name label and the value 42. So at this point, we know that the label is 42. It gets pushed down the tree. And if we are going to do the relabel, then we replace every leaf, the integer in the leaf, with a 42. And then we can compute it, and then we get back the result. If the result is just, if we have one synthesized attribute, then the result is the result of that attribute. If we can have more, so we can have a whole list of synthesized attributes, and then they will be returned in a tuple. It's also possible to, so now we have specified, for example, if you go a slide back, the initial value for inherited attribute with this clause, but it's also possible to leave that out. And give that as a second argument to the compute function. So then you say the initial value for this inherited attribute is this. Another feature that we have is that we can rename attributes. So we use the function rename for that. So in this case, we rename the label attribute with the index. So everywhere where label is used, we use the value of the index attribute at that point. So if we compute that again, then every leaf in the tree gets a unique number according to the index attribute. So this shows that we can reuse attributes and that we can really separate the definition of the attributes. So slide on. Pattern functions. So the pattern function determines what we are going to traverse. So the standard pattern function, so the pattern function can be given as an argument to the compute function. If you leave it out, we use a standard pattern function that traverses over recursive data structures. So it doesn't traverse over atoms and strings and the like. But you can define a pattern function of your own. And in this case, the example is, it's a contrived example for binary trees that only introduces patterns for balanced trees. So in case we have a node on either side of a node, we return placeholders for these nodes. And if we have a leaf on either side, then we return placeholders for the leaves. And otherwise, we don't return any placeholders. So if you apply that pattern function on an unbalanced tree and try to relabel every leaf in a tree, then you can see that so the sample tree was not balanced and it doesn't match, so it doesn't rename that part of the tree. Whereas if we have a perfectly balanced tree and we use the balance pattern, then it matches and then we get the placeholder on the right places and we can do the relabeling. It's a bit contrived, but then it gives a bit. With the pattern function, you can steer over what is interesting in your data structure, on what places do you want to have the attributes available. So, generating data. So when generating data, we again need a pattern function. We need to come up with a way how to generate places that we can fill in the next iteration. So in this case, we give a tree pattern function, and it takes attributes. So these are labeled inputs with attribute names. So in this case, if the attribute height is 0 and we have an attribute with value val, then we return a leaf with that value. And otherwise, we return a node with 2 placeholders. Then we need a height attribute, because that's what we use in the pattern function. So, and the height, we start out with, it's an inherited attribute, and we decrement it in every, whenever we traverse in a substructure. And we can use the following function, compute pure, which takes a list of attributes. So we have the height and an attribute called term, which is a special. So it's a predefined attribute that returns the actual term, because that's what we are interested in when generating data. And then we rename the value, so this attribute, to index. So everywhere where value is used, we use the index. And we can generate trees. So if we call tree with 3, we generate a 3 with height 3. And you can see that we can reuse attributes that we have previously defined. A different variant, so that is on the previous slide, the name was, it's not the previous slide, this is the previous slide. The name of the compute function for that, for generated data, was pure. We have also a variant called gen, which is specialized for the Quickcheck generator. It's a monadic, but forget about that. Then our pattern function should return not a term with placeholders, but a Quickcheck generator. So in this case, we use for a tree, we use a frequency. We choose more nodes than leaves, and we have an attribute, again, in this case called size. And if the size is larger than 0, then we are allowed to generate nodes. So we define the size attribute as follows. For every recursive data structure, we divide the size by 2. And instead of compute pure, we use compute gen. And we use the sized macro from EQC gen to control the size. A list of attributes again, the pattern function that gives returns a Erlang Quickcheck generator, and then so here we use the initial value of the inherited attribute and give it the initial value size that we get from the sized macro. And here we show we call EQC sample on the gen tree. So then we can generate binary trees. Yay. So the third and last example that I'm going to show, then we're going to do some scope checking. And imagine that we have this small Erlangish language. So we have variables, atoms, and integers, literals. So a variable is just a string. We have a match, assignment, we have a sequence, and we have a case expression. So, and I'm going to introduce this top down now. So I'm going to say, well, what is scope checking? Well, if I'm going to scope check in case of a variable, then the scope is okay if the X is bound. So I have an attribute bound with all the bound variables, and if X is an element of the list, then it's okay. in case of a match, then X better be not unsafe. So you've seen the error message now and again, I guess. And, well, the expression of the match should also scope check. And in the last, so the general rule says, okay, everything should scope check.
So bound is the set of bound variables in a given place, right?
Yes.
And unsafe is what?
Is also an attribute that we calculate. So these
What
are all unsafe variables.
so what are unsafe variables?
I'm going to show you what unsafe variables are. First, I'm going to show you the bound. So this is a top-down way of introducing. So instead of introducing bound and unsafe first, I'm going to say, okay, what does it mean to scope check? Now we have to implement or define the bound and unsafe attributes. So bound is in this case, it's a synthesized attribute. We start with the empty list. In case of a match, so then we get the bound variables from the parent node and give it to the expression. And as the result, so all the bound variables in that expression, we merge it with this variable and we give it to the parent node. In case of a case, then we get the bound variables that are in scope from the parent node. We give it to this expression and the result, so it might also bind variables that we give to the if case and the false case. And then we return the intersection of the bound variables in the true and the false case. And we're going to chain the rest. No.
So this is the variables that leak out of the case, right?
Yes.
So that's
Yes.
why it's the
Yeah.
intersection.
Yeah. Unsafe. We start with the empty list again. And in case of a case, we're going to first give it to the expression, then to the if and the false. But this is the interesting bit. So we keep the unsafe variables from the true and the false. And then we take the difference from the bound variables in the true case and the bound variables in the false case. And the other way around. So then if we say in one case we declare x is blah blah, if we do it in both cases then it's okay. But if they are not the same, then they are unsafe for later use. And we can, so this is an example.
Right. Could you go back to where you're actually using the unsafe attribute?
Here?
I still don't understand why we need it.
So it doesn't scope check if a variable is unsafe. If you want to,
But then if it's defined,
so perhaps
it's
this makes, so if we have, no, not this one, this one. If we have a case and we have a match, so in the true case we say x becomes 3,
right.
in the false case we say y becomes 4, and later on we're going to say x becomes 6. They say, oh, this is unsafe.
Right.
And then that doesn't scope check in this small examples. If we had x here, then okay, then we had a pattern match fail, because 3 is not 6. So this.
So that's why you need to remember the unsafe variables.
Yeah. So the point of this exercise was to see, okay, we can do some small type checking, and we check if variables are in scope and whether or not they are safe. So I've explained all 3 examples, and I've showed that attribute grammars allow for modular software development. And it's part of EQC Mini, so it's for free. And there's an implementation detail. We have interpretation and specialization. So we compared a small example to handwritten code, and I don't remember the number correctly, but was in an order of 200 times slower if you used attribute grammar. So that was, well, perhaps it's acceptable to pay a small penalty for having separation of concerns.
Why is it so slow?
Well, we didn't figure out exactly why, but it has to do with the interpretation. So that. And then we thought, well, Ulf implemented a very cunning specialization scheme that generates functions, and then it turns out that it's in some cases it's even faster than the handwritten code, because you can use fusion and get rid of intermediate data structures. Oh, and there's one more thing. It's not good news, because the syntax that the nice syntax that we showed, they've taken it away in R18. So that's not good news. So we have to.
So you based your stuff on something that was deprecated?
It's not even documented.
It was on the.
Okay.
What?
We know
I rest my case.
You mean I shouldn't have done that? Ulf shouldn't have done that? No, Ulf had this in the back of his mind, and I think he was searching for a project when he can use this nice syntax. It's the mnemosign database query syntax, which apparently nobody uses anymore, and well, they've taken it away. So we're thinking about how we can fix this. And one suggestion was that we can perhaps use macros and come up with this kind of stuff.
Okay,
Okay.
thank you.